All right, so here we are. I see a nice turnout here. Um, yeah, tonight we're starting a little late, and tomorrow night probably as well. Thursday we'll be having a recording instead of a live session, but then everything goes back to normal next week. So we'll be doing 6 to 9 Monday through Thursday. And so today, what we're going to do is some reviewing. After we look at the syllabus, what I'd like to do is go back and review some of the most important concepts from Stats 1, because, by this time it's possible you've started to forget what you learned, and there are certain concepts that you really should be on top of before we start the new material. That will be what we'll be doing tonight. And then maybe tomorrow we'll start something completely new. We'll see how that goes. So let me first pop open the syllabus, which I unfortunately didn't realize until I came over here tonight that I hadn't posted it until just now, a few minutes ago. So if you were looking for it, it is now in Blackboard. I just somehow forgot about it, but all the other notes are there. This is the only thing that was missing. So I just, there's just a few small things that we have to pay attention to. First of all, of course, this is an online class, so office hours won't happen in a normal way, but you can always ask for office hours and we can arrange a Zoom session at a time that's convenient for both of us. So my information is here, so you can write to me by email. And the dates are here, Monday through Thursday, 6 through 9. Now, my office is listed here, but obviously that doesn't matter because we're not going to physically meet in person. But instead, like I said, if you really do want to meet, it will be on Zoom, probably during the weekends. Okay. Um, what else do we need to know to get started? Well, we're going to use some Excel in this class, so hopefully your computer has Excel loaded on it. And also, as far as the calculator goes, the best calculator, as far as I'm concerned, is the TI-84, which I have right here. Okay. And or something similar to that. Now, because this is an online class, you don't have to have a physical calculator. There is an app you can get. I guess I should have put this in the syllabus. It's called Calculate 84. Let me write that here somewhere. And you can go download it. I think it's either free, or if it's not, it's very, very inexpensive. And something like $7 or something like that. That's what I think. I'd have to double check, but Calculate 84 is the name of the app. You can download it even as soon as now. And in fact, I'll show you what it looks like on the phone. Let me see if I can find it. And the beauty of it is that it really does a good job simulating the actual physical calculator. Now, of course, I know everything is backwards here, but the app looks, well, I know it's hard to see there. That blue one is it, Calculate 84. It looks like a little calculator. Okay, so if you don't want to spend the money on a brand new calculator, you can go ahead and download this. During the school year, what I recommend people do is they use that if they forget their calculators, but I would insist that they have a physical calculator for their exams. But here, the exams will all be online, so it really doesn't make any difference. Okay, so you can do either one. Right? Now, if you happen to have an Inspire, which is a much more advanced calculator, that's fine too, but I don't really know how it works. So if you have questions, I'm not the one who would help you with it, okay? So if you do have an Inspire, you may have to do some reading online to look up the functions. They'll be similar to the Chai 84, but not identical. It can be a little confusing because there's so much going on there. So that's the calculator. So Calculator 84, Excel, of course, but I'm sure everyone has Excel. If you don't, you should be able to get a free copy from the school. Microsoft has cut a deal with just about every school in the country that lets you use this as long as you're still in school. So that shouldn't be a problem. Now, having said all that, there's one thing that you need to know about this class. All the assignments will be done online through a system called MindTap. Now, you may have used it in another class. If you have, you may not have to pay for it this semester. They have generous deals as far as that goes. If you've used it before, especially if it was in the spring, you may not have to pay for it again. But if not, um, it's unfortunately going to set you back about 120 bucks. But that includes the MindTap system, but it also gives you access to the textbook. And if you use MindTap in the fall for another class, again, you might not have to pay for it. We'd have to call up Cengage and ask them for the actual rules about that, but they're usually pretty generous about that. What is it going to get you, and how do you get into it? Well, if you go into Blackboard, you'll see under this folder, getting started with MindTap. I believe this link here is the one that lets you sign up. Now, my system will react differently from yours because I already have it. So um, let's see what happens here. Or it may not work at all. So I'm pretty sure that's where you will find the instructions to set up your MindTap account. And yeah, I don't know what's going on here. Let me just click that off. I don't know what it's doing. This, I think, is supposed to be the instructions. So this is the first semester that I'm using this particular setup. So I don't know exactly what these three folders are doing. But if you're having any issues at all with it, you should let me know and I can have Cengage get in touch with you. You may not need it for a few days anyway, or at least into next week, because since we're just starting, the first assignments wouldn't be due until at least a week from Friday anyway, or Sunday, I mean. All right, so these are actual physical instructions, okay. But this is probably the link then, where you just click it on and it'll ask you to pay for it. And that's really all you have to do. I mean, it's all set. No, this is the actual. No, see, this is what this happened, I think, because I already have it. That's yours will almost certainly show up in instructions for how to pay for it. So give it. Oh, also, it has a free trial period, which I think is 14 days, or it might be 10. So in other words, you don't have to wait until you actually have the money to pay for it. You can start right away, and then hopefully you can pay for it within the next 2 weeks or so. And then that way you'll be able to use your free trial while you're waiting to get the money together. And now keep in mind too that, textbooks, ooh, they're so expensive these days. 120 bucks sounds like a lot, but that's really less than you would pay for a brand new textbook. And you're getting it with this too. So it's not that bad. Okay. All right. Not that bad. So that is something, these are the things you need to have for this class. Like I said, all the assignments will be in the Mind tab, as will the exams. Okay. So I don't think they're in there now, but I'll be posting them so that you can work on your exams, and we'll explain that as we go along. Now, what I'm going to do here is just open up my copy of Mind Tab, just so you can see what it looks like. Okay. All right. So if once you get it set up, it'll look something like this. So you sign in and sign in. My courses, and you'll probably just have the one. I have quite a few actually. And so, of course, we are economic summer statistics 2. Here's the book. And keep in mind, since this is stats 2, of course, we're not going to start at the very beginning of the book. This is a 2-semester textbook. We're actually going to start with chapter 9. Now, you'll come in here and you'll see a bunch of chapters. These are the ones we'll be covering. And if you look over here, this is our calendar, I guess. And if you click it on, you'll see what's due. Like, for example, here you can see that nothing is due until the 12th. So that's actually 2 weeks. or so away. So you'll have plenty of time to get started with the assignments for chapters 9 and 10. Now, they do sometimes give you these estimates here of how long they think it'll take, but I've been told by students that these are a little bit maybe exaggerated. Like a lot of them told me that it didn't take as long as it says here. So you have to use your judgment when you want to start working on these, but they're set up so that you can do them a little here and a little there. You don't have to do them all at once. You can do them as, do a little every night if you want, and you can save your results. In fact, let me open one up so you can see what it looks like. And when you're finally done, you can submit it. And another beauty of this setup is that it'll allow you up to 3 attempts at each question in case you make a mistake. You can try it again and again for 3 tries, and then it'll keep the best answer. So it's designed to be very helpful, encouraging. It's not meant to be dreadfully difficult. Sometimes they're multiple choice. Sometimes they're fill-ins, sometimes there's calculations involved, and sometimes it has its own Excel spreadsheet that you will download and use that to finish the assignment. Some of these only have one question, some of these have several questions. They're all a little bit different. Yeah, so okay, let's see how long this is going to take. Here we go. So this one is a question about the normal distribution. And, something you've seen before, but we're going to review it tonight. And it's just the one question. And if you get confused, if you're not sure what's going on, it'll give you, like I said, 3 tries to finish it. And that should help quite a bit. And again, you can do it in stages. You don't have to do it all at once. Even the tests will be set up so that you can do them in stages, but you'll have more restrictions on how many times you can try it. So, but the exams will be just like these assignments in the regular assignments in MindTap. Okay. So everything is here, everything you need. And also another thing I want to mention is that all of the assignments are currently open, except for the exams, which I'm working on, which means you can start as soon as you want. If you feel like you can start and do like a bunch of them right up front, that's fine. There's no penalty for finishing early. So they're all open. And if you just feel like getting started, that's fine. Don't worry about it. They're already open. So in other words, everything is designed to be as simple as possible, as easy and user-friendly as possible. And I think you'll learn a lot. The MindTap system, if you've never used it before, it gives you helpful hints. It lets you check your results before you submit it. And it also gives you links back to the book if you need them. And sometimes it even has videos that you can watch to help yourself understand the material. Okay. The only thing you have to watch out for is that you must read the instructions carefully, because often what will happen is they'll tell you like how many digits of accuracy to use. If you don't pay attention to that, it'll mark you wrong, even if you have the right answer. So just be careful with the way the questions are worded. Right? Just remember that. So other than that, everything should be fine here. And we have 6 weeks, I believe, before everything has to be done, which is maybe less than half a normal semester, but not that much less. So the pace won't be extremely rushed, like some summer classes are, but it will be more accelerated than what you're used to during the school year. All right, what else do we need to go over? Let's see. Now, the rest of this is the usual language. They're reminding you that this is the second half of a 2-semester course. So it's understood that you've already had Stats 1, but, of course, you might have started to forget. That's why we're going to review a little bit tonight. And once we're done with that, we'll dive right into a topic called hypothesis testing, which really is something we'll be doing throughout the entire course. Okay. It's something that you'll see constantly in statistics. So we'll start at the beginning and take it from there. And when we're done, we'll be using regression analysis, which is one of the more important techniques in statistics, especially for doing research. Okay. And to the extent that's possible, we're going to do a lot of these techniques in Excel because the more you know about Excel, the better off you'll be. You may already have used Excel in your other classes in Gabelli. And well, the more you learn, the better. Okay. We're going to use it for slightly different purposes than your other classes. But again, the more Excel skills you have, the better off you'll be. And also, I would like to remind you that according to the terms of the syllabus, which I'll show you down here, you'll actually get a grade on your Excel assignments, although only 10%, because you may not have had any background in Excel. But, it's just what we'll do is as we go along, I'll collect your Excel work and then give you a grade. The Mind Tap is the majority of the grade, as you can see. And then we've got the two tests and the final, which sounds like a lot, but I don't know. I think you'll find that it'll fit in 6 weeks. Okay. Now, the way this course is set up, all these lectures that I'm giving you will all be recorded and posted in Blackboard. So that way, if you miss something, which is entirely possible during the summer, your schedule can get very strange in a hurry. You may have to go away. You might just not be available. So if you do miss a class, the videos will all be posted here in the respective chapters. You can watch them at your leisure. Okay. And then also I'll be writing notes, as you've seen already, as if I were writing on a whiteboard. And these will be saved and stored on the Blackboard as well. And then the PowerPoint slides that we'll be basing our notes on are already in there, along with some of the Excel spreadsheets that we'll be working on. Okay. So it's all here. The only thing that was missing until a few minutes ago was the syllabus, which I completely forgot about, but that's done. So let's see. I'm wondering if there's something else I'm overlooking. I don't think so. Yeah, some of this language doesn't really work with an online class. I mean, it's talking here about not disrupting the class and all this and that, but of course, online, that's not going to be an issue. But basically, everything you need to know is right here. And you can see now all of this, it doesn't look like a lot of chapters, but it's very complicated material. And when you're done, you'll be in really good shape with your statistics skills, and you'll be prepared to work on major projects in your other classes, do research, and many other things. All right, now I'll tell you what, let's get started with my review. Now, I wrote these notes myself. Um, I am of the opinion that before we go into stats 2, you want to make sure that you are comfortable with the normal distribution, confidence intervals, and students' t distribution. So because, again, you might have started to forget how these work, we're going to go through these first, and when this is done, then we can start something new, which is chapter 9. Now, another thing I just want to mention too is that, the stats courses that we offer, there can be slight differences between them. It's been my experience that not every professor gets all the way through chapter 8 in stats 1. And chapter 8 is confidence intervals, but it's also the case that some professors get really ambitious and they push ahead and they've already done confidence intervals or hypothesis testing in chapter 9 in stats 1. So I don't know which camp you fall into, but no matter what happens, we'll be doing it all correctly here. So we'll start with a review session. It should sound very familiar, everything we're doing. We'll do some calculator work. And then at some point, we'll turn our attention to chapter 9. Okay. So we'll start by reminding ourselves that there are actually two different kinds of probability distributions. And we're not going to review, actually, hold on one second. It looks like I only covered one of them in there. There are two basic types of probability distributions. And you probably remember them. If you don't, as soon as you see them, you'll recognize them. and they are discrete and continuous. Now, the discrete ones include binomial and Poisson. What separates them is that with these distributions, number of possible values of the random variable x is finite. So like if you remember from the binomial distribution is a case where an experiment is being repeated, where each trial is independent of the other trials, and the probability of getting a success, as it's called, is the same on every trial. And there's only two possible outcomes to each trial. That's really where the name comes from, binomial. And so if I flip a coin 10 times, for example, and I want to know the probability of getting three heads, that's a job for the binomial distribution because I can only have up to 10 heads, and I want to know the probability of getting three. Poisson is the one that involves the passage of time. For example, how long will it be before the next phone call arrives? So those we don't need to review here because we won't really use them again in Stats 2. But you can go back into the book and review if you need to because it's all in the same textbook. The ones we want to focus on here are the continuous ones. And so you probably all for sure you would have seen the normal distribution, the t distribution, and possibly the continuous uniform distribution. Now we're not going to really need the uniform in this course, but we will need the t and the normal quite often, as a matter of fact. And what's different here is that with these distributions, the number of possible values of the random variable x is of course infinite. What else is there besides finite and infinite? That's what really separates it. So the continuous ones are obviously more complicated. They really do require us to use the calculator or Excel. The finite ones or discrete ones we could do by hand if we needed to, because we do have formulas, but here it's not really practical. So we end up using the calculators. Now, of all of these, the one that really is probably the most important is the norm. Oh, so here we go. So I wrote these in my notes. X is defined as the length of time until the next phone call arrives. Now, the number of possible times is actually infinite because it has a fractional component. It's not required to be an integer, like the number of flips of a coin. So therefore, the number of possibilities is literally infinite, and therefore X is a continuous random variable. Now, the probability distribution that is associated with that continuous random variable is known as a probability density function, and it is represented as a curve of some kind. And like here's an example of a discrete distribution. For this one, we use a graphical device called a histogram, which is a series of bars, each of which has a height equal to the frequency with which it occurs. So whatever this distribution is, which I completely made up, you can see there's only 5 possible values of x or a random variable. The probabilities are listed next to it. The heights of these bars represent the probabilities. But this is only made possible by the fact that this is a discrete distribution because I have a finite number of bars. But if I had a continuous distribution, the number of bars would need to be infinite. So I would replace that instead of with bars with heights of these lines, which give us a curve. Okay, so no more bars, we have curves. And the value of interest for us is the area under that curve between two given points. So whatever this represents, the probability that x is between 2 and 3 would literally be nothing but the area under this curve between 2 and 3. So if we have a formula for that curve, we could easily calculate this ourselves. If not, we can use the calculators. Okay. And yes, the time until the next phone call. By the way, the reason why um, one of the interesting consequences of being continuous is that there's an infinite number of possibilities, and each one individually has a probability of zero. Because if not, you'd be adding up a bunch of large numbers and you'd end up with infinity. So instead, we define the probability of a specific result as zero, and instead we focus our attention on intervals. Like here, the probability being between 2 and 3. That we can do. The probability of it exactly equaling 1.7, that we can't do because it's just going to be zero. Right. So another consequence of that is that we don't make a distinction between um, less than. You notice how these are the same. In other words, strictly less than is the same thing as less than or equal to. And the reason for that, if you look up here, you'll see that less than or equal to is actually the sum of being strictly less than and equal to. But if equal to has a probability of zero, that means these are equal to each other. Less than or equal to, strictly less than, they now mean the same thing. So with the continuous distributions, we do not have to make a distinction between the two cases. With discrete, we most certainly do. Right then. Um, so the continuous ones that we need for this class are the normal and the student's t. We will, by the way, introduce some new ones in this course. Okay, something to look forward to, but these we need to know before we go any further. Here's our old friend, the normal distribution. You recognize it as the bell-shaped curve. So we know a couple of the key properties. The mean is represented by the Greek letter mu over here. And then the Greek letter sigma is the standard deviation. So the mean is at the center, and the curve actually covers the entire real number line. In other words, it goes all the way down to negative infinity and all the way up to positive infinity. We have symmetry about the mean, which means the left and the right are identical to each other. And the total area under the curve, because this is a probability distribution, is defined to equal 1. Okay, just 1. It may not look like it, but that whole area under there is defined to equal 1. Now that curve has a formula. I'll show it to you, but you don't really need to know this formula. This is what it actually looks like. And if you notice, there's two key variables in here, sigma and mu. In other words, those two values are what we need to know to characterize the behavior of the normal distribution. In fact, let me show you some graphs. Here are two normal distributions with the same standard deviation, which means the same shape. Their locations are different because the one on the left has a mean of 0, the one on the right, it's 10. Okay, so they're identical shape-wise, their location is different. So the mean tells me where they're located. Whereas the standard deviation is the shape. A big standard deviation means that it's more spread out about the center. It's still symmetrical, but it's not as tall and it is more spread out. So if they have the same mean, the only difference between them is how spread out are they, which is measured by the standard deviation. So in principle, there's an infinite number of normal distributions, each with its own unique values of mu and sigma, but there's one case that's particularly important, and that would be the standard normal. Now, why did I put all that red on there? Because I want to make sure you don't forget this. Here, the mean is 0 and the standard deviation is 1. That is our standard normal distribution. And this one is so important that it gets its own letter. Okay, most random variables are written with an X. This one is written with a Z. So you have to recognize it when you see it. And that's quite a badge of honor to say, listen, you deserve your own letter. Well, that's what's happening here. Okay. Now, you might also remember that you can calculate the probability of being within a specific number of standard deviations from the mean. So the normal curve, the standard normal, z, the standard normal random variable, has approximately a 68% chance of being in this range between the mean minus one standard deviation and the mean plus one standard deviation. Okay. Now, we will later on remind ourselves how to look up the exact probability in the calculator. These are just rules of thumb. For 2, the probability jumps up to 95.44% approximately. And then, oh, look at 3. Almost the entire distribution is contained within 3 standard deviations. All right. Now, I did mention tables in here. You may have been exposed to tables in Stats 1. If you were, the tables referred to the standard normal distribution. For example, here, and by the way, they only show less than or equal to probabilities. So how would you look up the probability that z is less than or equal to 1 on a table? Well, you need to look for the intersection of z is equal to 1 and 0.00, and you'll come up with 0.8413. Now, while we're talking about this, why don't I show you how to do this in the calculator? I know that's one of our plans for tonight. So hopefully by this time you have found your calculator, or you've downloaded the Calculate 84 app or something along those lines. Maybe the cat knocked it under the couch, but you found it. That's okay. So how would you calculate something like this? The probability that z is less than or equal to 1. It's a terrible drawing. I'm actually writing on a tablet and it works fine, but drawing is very challenging on it because it doesn't have its own screen. It's like a flat piece of plastic and you're writing on the surface and it corresponds to what you're seeing here. So you're looking one way and writing the other way, and it can get a little challenging. Okay, so um, that's why sometimes it's going to look like it was drawn by a fourth grader, but here we go. Remember, this implies that mu equals 0 and sigma equals 1. Well, I want to know that probability, and it would look something like this. So if you go to the TI-84, you're going to hit, to get to this menu, second vars. And vars button is directly to the bottom left of the arrow keys. And then it's going to show you a huge list of formulas. For this, we want number 2. Normal CDF. Now, directly above it, there's another one, normal PDF. We will not be using it in this course. All right, so choose this one. And it's going to ask you for 4 things. Now, what does that mean, lower and upper? Well, this interval here would be, you can think of it as being between 1 and negative infinity. Now, there is no button in here for infinity. So you have to do the following. Just make sure you use the negative button, not the subtraction. Directly below the 3. Second, hit a comma, which is directly above the 7, and then the number 99. And all of this should appear in your window as E90, which stands for 1.0 times 10 to the 99th power. Oh, yeah, sorry, negative 1.0 times 10 to the 99th. I almost forgot the negative. That's not negative infinity, but it's awfully close. The upper limit is simply 1. Now, because we're dealing with the standard normal distribution, all 0 and 1 here. Okay, now it's probably already there. Usually that's what it sets up for you, unless you tell it something else. All right, and you run through all that. And we normally round these to 4 places. So you can put 0.8413. It's a little getting used to, but that wasn't hard at all, was it? I think you'll agree it's easier than tables. Now, the other problem with the tables is they're only set up for the standard normal distribution. If you have another one, you have to do something a little different. What else do we have here? Ah, so imagine now this is a different situation because we're not dealing with standard normal, or although we can convert it into that form. We have an exam with a normal, where the scores are normal. The mean is 80. Standard deviation is 8. And so they want to know 88 refers to one standard deviation above the mean. Now, it may not seem like it, but that's what we just did up here. With the standard normal, because the mean is 0 and the standard deviation is 1, this 1 is actually interpreted as one standard deviation above the mean. So whatever we get here, it'll be the same number. It's just different units. It's scaled differently. It's like the difference between Fahrenheit and Celsius. So to come up with this, and by the way, because we're not dealing with the standard normal any longer, write it like this, and then we can go to the calculator. The lower limit is negative infinity. Which again is expressed as negative second comma 99. Upper is 88. Now here's where you have to watch it. By using these numbers, you've got to make sure that you've got the same mean and standard deviation. Don't leave it at 0 and 1. Otherwise, of course, you'll get the wrong answer. So you plug everything in and you'll say, wait a minute, it's the same. Well, it is the same because it's the same number of standard deviations above the mean. The units are irrelevant. The fact that here we've got 80s and the other one is zeros and ones, it doesn't matter. It's the distance away in terms of standard deviations that really matters here. All right, I'm going to plug it in. And lo and behold, it's the same, 8413. It has to be. All right. Now, what else do we have here? So we don't have to do every single one of these examples. By the way, the instructions are right here in case you haven't done this before. In the Chai 84s. I know some stats classes, they refuse to let the students use the calculators. I was not one of those professors. I always let people use the technology, but if not, if you're not familiar with this, these are the instructions you need. And the explanations are all here. I also reminded you how to enter negative infinity and positive infinity. By the way, this comma means literally type a comma. Sometimes people get confused about that. The comma is found directly above the 7. All right. So yeah, it means second and then a comma and then 99. And this is what we got. All right, now let's remind ourselves some of the key properties of the normal distribution. Well, here are the standard normal. The whole area under the curve equals 1 because it does represent a probability distribution, and that means the total of all the probabilities has to be 1. It equals 1. All right, what else do we have to know? Now, by the way, because when it's standard normal, the mean in the center is 0. So area above the mean and the area below add up to 1, but they're also equal to each other, which implies that on either side of the mean, we have an area of a half. Oh, sorry, this is supposed to be 0. Probability is equal to 0. Less than or equal to is the same as the probability being greater than or equal to 0. And they each individually now are equal to half. All right. What else do we need to know? Oh, well, one of the implications of these adding up to 0 is that, 1 rather, is that if you have a problem where you're calculating a less than or equal to, no, greater than or equal to, is that let's say I'm doing this. This is, it has to add up to 1 with this. And so therefore, these add up to 1. Is that if I wanted to know the area above 2, I just subtract off from 1 the area less than or equal to 2. Okay, so I can figure out any of the probabilities I need. On the calculator, this isn't really necessary because, like, if I just want to know something like this, I would do lower is 2, upper is infinity, Oh, sorry, not second, second comma 99. What we're after. So 2 up to infinity. And then, of course, since it's the standard normal, you would end up with 0.0228. It does mean then that the probability that z is less than or equal to 2, 9778, which is this piece. Okay. So without having to look at the calculator, you already know that. What else do we need to know? Uh, you don't have to go through every single one of these. These, just put a bunch of these in here in case you would need the practice. Now, back in ancient times when there were no calculators and only tables were available, if I wanted to calculate the probability of a normal random variable that wasn't standard normal, the only option I had was to convert one to the other. So, and then use the tables. And if I did, this is the formula I would use. Okay, so, let's say that, let's see a case where we want to do this. That exam scores are normally distributed with a mean of 70 and a standard deviation of 5. Just a little bigger. Now, I would like to know, for example, what is the probability, oh my God, it's small again, that a randomly chosen exam score is less than or equal to 60. All right, so again, we have a couple of ways of doing this. So here's how we can think about it. In a 70, standard deviation is 5. So what do these numbers represent? The mean plus 1 standard deviation, mean plus 2, mean minus 1 standard deviation, and the mean minus 2 standard deviations. So this is our x. You could then define the equivalent standard normal distribution. Zero, one, is 2. And they would be interpreted the same way. This is the mean. Wow. Now, it's clear from this graph. So in other words, the probability of getting below 60 is the equivalent of getting z less than or equal to -2. Okay. It's again, it's kind of like converting from Celsius to Fahrenheit. They're both the same thing. It's just one is, you have the 32 and multiply by 1.5, 1.8 rather. So anyway, I can either, to get this, answer this question, I can either calculate the probability that X is less than or equal to 60 in the calculator, or I can calculate the probability that Z is less than or equal to -2, because it means the same thing. And ultimately that brings me to here. It's a very small probability, as you can see, 0.0228. I go from the top to the bottom. If you apply this formula to these cases, you'll see that it works. If I subtract from one of these, I subtract 80 and divide 70 rather and divide by 5, it will give me the equivalent standard uh, score or the z-score. Calculators the way they are, you don't really need to bother about this. You can just choose whichever one you're already using. Just make sure you put in the correct mean and standard deviation, okay? Excellent. We need to review for the normal. Let's run through this one really quickly. The return to a stock is normal. Mean is 5%. Now, by the way, when you're dealing with percentages, it's usually easier to convert them into decimals. That's just my opinion. You don't have to, but I prefer it that way. So they'd like to know the probability that over the coming year, the stock will first will do greater than or equal to 0.04. So on your calculator, you can do second bars, 2, normal CDF. And then, of course, as you remember, it's the lower. So here the mean is 0.05. That's what we're looking for. Lower is 0.04, upper is infinity. And don't forget though, here the mean is not 0, it's 0.05. And here, 0.02. Then, oh, and don't forget, this is second. You'll know you've done it correctly if it shows up as E99. And then we have 0.05, 0.02, and we'll get 0.6915. That wasn't so bad. Part B, 8% or more. Oh, you know what? I just realized I goofed. I just did 4% or more, and it asked for less. Oh, all right. I'll tell you. Let's go. Well, let's do it. I'm not going to erase this. There's no reason. This is a good example. Um, I'll call it A again. But you know what? We don't have to bother. I'll tell you why. Because this area that we just calculated incorrectly is 6915. What does that suggest about this piece that we really wanted? It's 1 minus 0.6915. So Uh, so in other words, the probability that it's less than or equal to 0.04 is simply 0.3085. We don't have to start all over again. Okay. This is one thing I've noticed about teaching online. When I'm using this tablet, it's a nice tablet and all, but the problem is the amount of information that's visible at any one time is not that much compared to the whiteboard, where I can see like two or three problems ago all at once. So that's why very occasionally I notice that I have accidentally written the wrong thing because I couldn't see what the numbers were. So I'm not making excuses, but that's just the reality. So I can see why that would have happened there. All right. So no harm done. 8% or more. Now let's do this one. All right. So what are we looking for? So clearly this is going to be a fairly small probability. We're quite a bit ways out into the right tail. I remember in the problem, they told us that the mean was 5 and the standard deviation was 2. All right. So if you plug those in, you'll get 0668. Like I predicted, it's quite a small number. Okay, you're getting way up there into the right tail. And then the third one is an in-between probability, I believe, between 4 and 7. Yeah. Okay, so second vars. All right. Um, so we're between. Now this time we don't need an infinity. It's 0.5328. Okay. All right. So I think we're in pretty good shape with the normal distribution. So why don't we move ahead now to the confidence intervals, which I was just thinking, I think I goofed here. The t distribution should really come next because the confidence intervals can be based on either the mean or the standard normal. So I'll tell you what, let's call an audible here and let's move on to the t distribution, and then we'll come back and revisit the confidence intervals. I must have been in a hurry or something, but we'll look at the t distribution. And the t distribution has kind of an interesting history. There it is. No, here it is. So a lot of these distributions that you're learning about were developed by mathematicians throughout the centuries. This one is a relatively new invention. It came about in the early 20th century by this gentleman, William S. Gossett. And Gossett wasn't a mathematician as such. He was the head of quality control at the Guinness Brewing Company. And he was studying sampling techniques. So, in other words, when you're making a product like beer, which technically is alive because there's yeast in it, lots of things can go wrong. So it has to be tested to make sure it goes out to the public safe and it tastes the way it's supposed to. The problem is if you test all the time, you constantly test, you could swallow up all of your profits. So he was trying to figure out a way to make valid tests with a relatively small sample size. The problem is the normal distribution is not appropriate for such a situation. So Gossett realized he'd have to create his own distribution, and he published it with not his own name. He published it under the name Student. Now you're probably wondering why would he hide his own identity? Because when Gossett arrived at Guinness, his predecessor had apparently been involved in industrial espionage, stealing company secrets. So they told Gossett, listen, going forward, if you want to do research, do not publish it under your own name. We don't want anyone to know this is coming from Guinness. And so that's why this became necessary. So it came to be known as the T or students' T distribution. Okay. And how is it different? Well, I'll tell you what. Let's look at a graph. Um, this is generated by a computer program called MATLAB, and which is a scientific programming package. Let me just draw my own little picture of it here. So this is the standard normal distribution. Equivalent T distribution. Oh, okay. It'll have to do. It's not perfect. But now maybe let me try it again. Much better. Okay, wonderful. So here's what you're supposed to notice about this. Between the two of them, uh, both have a mean of zero, metrical about the mean, and what separates them then is that the t distribution is more spread out, standard normal. In other words, there's more in the area in the tails and not so much in the center. Okay. And this is a consequence of the fact that the t distribution has a larger standard deviation. They're normal. Now, here's where it gets potentially a little bit confusing. If you remember, the standard, well, the normal distribution in general is characterized by the mean and standard deviation. P distribution is characterized by one single value, which is called degrees of freedom, or DF. Wow, what is that supposed to mean? Well, the degrees of freedom is different for every application, but it is always related to the sample sizes that are used in whatever testing we're doing. Okay. So in other words, it's a function of the sample sizes that we're using. And so what's interesting about this is that the greater the number of degrees of freedom, resembles the standard normal. In fact, I'll show you that in the next graph. These graphs right here, the green curve is the standard normal. The blue is the T with 5 degrees of freedom. If I jack that up to 30, I get this. And you can see now they're very nearly identical to each other. Okay, so the degrees of freedom is what separates one T distribution from another. Now, as far as the moments go, remember the concept of moments. Moments are measures that describe the properties of a random variable. Typically, we have the mean. All right, I shouldn't say that. The ones that we usually focus on are mean and variance are two moments. The standard deviation is not actually a separate moment. It's the square root of the variance. So technically it's not a third moment. But there's altogether 3 that we need to know. And so if you remember the standard normal, actually, I'm going to need some space here. Hold on. The mean is mu equals 0. Is represented as sigma squared. Over here, it has a formula which involves 2 new Greek letters that I'll just show you right now. This is the Greek letter nu, and it represents degrees of freedom. And then the standard deviation is, of course, just the square root. Oh, by the way, I almost forgot. These are both 1 for the standard normal. And I just like to point out that no matter what nu is, it's always going to be greater than one because the denominator is less than the numerator. And this is what accounts for the fact that the curve is so spread out. Okay. Right. So now what we also need to remind ourselves is how to look up values in the calculator for the t-distribution. So let's say the value of a t random variable or a t-score associated with. So by the way, this is the t with 9 degrees of freedom. They'd like us to find the right tail area where 5% is here. And so what we'll do is we'll write the degrees of freedom up here and the tail area here. So here's what you have to do. Go to your calculator and type second vars. And this time, the menu item you want is number 4, which is INVT, which means the inverse of the t distribution. And it's going to ask you for only two questions, area and degrees of freedom. Now, when it says area, be aware what it really means is not this area that we're actually looking for, but this area to the left of that point. It's always geared towards left tail areas. So you're going to put not 0.05 in here, but 0.95 and 9 degrees of freedom. So if you do that, you're getting 1.833. That's the cutoff point between the upper 5% and the lower 95% of the distribution when we have 9 degrees of freedom. So, all right. So that now we can go back and reintroduce confidence intervals because we have enough background in the t distribution. All right. Now with confidence intervals, we're going to do specifically confidence intervals about the mean, the population mean. We can also apply them to other values as well, but we're going to stick with the mean right now. What are we trying to do here? We're trying to construct a range of values within which we believe the mean actually falls. Okay. We know that X bar is a point estimator, as it's called, of mu, which means it's a single value, which is fine as far as it goes, but a confidence interval is even more valuable because it gives us a range of possibilities. Ah, that's what we're trying to do, an interval, not just a single number, but an interval. So there's two possible cases we could run into here. Two. So for case one, we're going to use the standard normal distribution. How? Well, the interval will look like this. So everything here is familiar. This might not be. What is that all about? That's our level of significance. So 1 minus alpha is our confidence coefficient. Multiplying it by 100 turns it into our confidence level. So let's say the alpha is 0.05, then 1 minus that, our confidence coefficient. And then multiplying it by 100, and that's our confidence level. And then we choose that. Okay, we're the ones who decide what level we want. So if we look at this thing, by the way, let's get some practice looking these up. Oh, I know what happened. I hit the wrong key. This is our z-score. So let's stick with the example of 95%. Minus alpha is 0.95, alpha is 0.05, alpha over 2. And then looking for this point, and how do we find it? Second vars, and this time it should be number 3, which is INV norm. it will ask you for the area. And that again is the left tail area, which means this part on the left, which is 0.975. And then the mean and the standard deviation are 0 and 1 because this is the standard normal distribution. If your calculator offers you this tail option, make sure that it's set to left. If not, don't worry about it because it's already set to left. And then go ahead and calculate that, and you'll see that it's 1.645. Not 1.645. It's 1.96. So that would be part of that formula. And what else? Just some terminology though. This ratio is called the standard error of X bar. And this entire expression is what we're going to call the margin of error. This is our point estimator. That put together gives us our confidence interval. Okay. There's a lot going on here. Let's see if there's an example. Yes, there is. Um, Fund holds a portfolio consisting of 500 stocks. The annual rate of return is normal. The standard deviation is 20. Now that implies that they're talking about this population standard deviation. And don't forget, we're turning decimals into percentages. Sorry, percentages into decimals. The sample is 10. We're going to use the Z scores or normal, standard normal, because we know sigma. Sample is 10. The sample mean is 0.08. So if we wanted to construct a confidence interval at the 90% level, do document is running out of space a little bit. Let me do something here. All right, then. So here's what we would have to do. So the X bar is, I forget already, 8%. For 90%, this is 1.645. Discover in a minute. Um, Sigma is 20%. And oh, and the sample size is just 10. Remember, we said we want a 90% confidence interval. So that's where that's coming from, meaning a right tail area of 0.05 and a left tail area of 0.95. It's going to be 1.645. So now we just plug everything in. That's really the only tricky part. So let's plug them in. 0.08, plus or minus 1.645. Here we have 20, and this 10, I believe. It seems to have disappeared here. There it is. So usually the first step is to figure out the margin of error. And whatever it is, add and subtract it from the mean of 0.08. So what does that leave us with? And that's just shorthand for saying both add and subtract from the mean. Let me just double check this. 0.08 minus, that's it. So in other words, what we're saying is that while we think that the mean is 8%, we're 90% confident that it's actually somewhere between minus 2.4% and positive 18.4%. Now that's a wide range, but at least it gives us a sense of how inaccurate or accurate our mean estimate is likely to be. Okay. Now we can also do 90 5 and 98, 99 rather. Now, since you've seen this before, we don't have to go through every single one of these examples. Here you would replace this with 196, and then the rest would be the same. All right, so I'll just put that in there. And for 99, we'd replace the z-score with 2.576, and then you plug it in, and you've got your respective results. Okay. So what about the cases where sigma is unknown? That's going to introduce the uncertainty associated with our results. Therefore, the interval has to get a little bit wider to make up for that or show us that. So what we're going to do is lean on now the t distribution. And by the way, in reality, this is the case most of the time. You're not likely to know the population standard deviation because that would mean you've measured the whole thing. So it looks a lot like the other one, except you've got t instead of z and s instead of sigma. Okay. Now, this notation means degrees of freedom and tail area. But you see, it's the same basic idea. This is my margin of error. And actually, let me make that clear. The whole box is the margin of error. Just this piece um, is a so-called standard error. Of X bar. All of it together gives us what we're looking for. So let's do one of these. The rest are in the slides anyway. Here's a 90%. Oh no, that's the previous one. Here we go. University has 10,000 students. The GPAs are normally distributed. A sample of 10 is chosen. And the sample mean is 3.10. Sample standard deviation is 0.25. As soon as you see that, you know to use the t distribution. Okay? That's all you need to know. Well, let's try 90% confidence interval. Actually, let's do 99 just for the fun of it. That t score, alpha is 0.01, alpha over 2 is 0.005. This is 1 because these two add up to 100% if they're expressed as decimals. We have a sample size of 10, so we have 9 degrees of freedom, 0.5% in the tail, which looks like this. But we're going to use this area because that's what the calculator is set up to do. Actually, this one is 4, sorry. of freedom. The area is in the left tail, which means, as you can see from this graph, 0.995. Combined with 9 degrees of freedom gives us 3.25 approximately. And that's what goes into the formula as the z-score, or the t-score rather. And then we fill in the rest. Right, let me erase some of these boxes and lines. All right, so let's get our data together. So remember, the mean was 3.10. Standard deviation was 25, and n is 10. Say that right? Yes, 0.25 and 10. Let's calculate the margin of error first. Zero point 257. And let's see what that leads us to. 2.843 up to 3.357. That's my 99% confidence interval. But the mean is in there somewhere. If you want to go through the others too, you can. So that, yeah, you might run into this in chapter 9. Anyway, we may as well run through one of these. This is the proportion of a population or a sample. Yeah, the way the book writes these, yeah, okay, so P is meant to be the sample proportion. So what is that? Remember, before I mentioned that those two cases we just considered with confidence intervals for the population mean. Here, instead, we're interested in the proportion. So now every book has slightly different notation. This book uses P, plain old P, for the sample proportion, which in turn can be interpreted as X over N. N is our sample size. And X is the number of elements in our sample with a specific characteristic, whatever we're looking for. So then the actual formula for the confidence interval is right here. So once again, now, by the way, here's an interesting side note. With the proportions, we never use the t distribution. It's always based on the standard normal. Right? And that does make things a little bit simpler for us. So this is the only case we have. Okay. So that does make things a little bit simpler. So let's look at our example. Um, and of course, the terminology is the same. This piece under the square root is my standard error. Higher expression here is my margin of error. Standard error P, that is, and margin of error. So here they're telling us a random sample of 105 fast food restaurants. Of these, 74 of these offer at least one vegetarian option. That's what our characteristic is, the ones that offer the vegetarian choices. So P bar, or P rather, is whatever that ratio is, 0.7048. All right. Now they're going to ask us to do a, oh, okay. Well, let's just pick the 95%. We don't have to do all three because again, you've seen these before. Um, so now the great thing about the standard normal is there's only really three cases we need to worry about. And you'll see them over and over again. After a while, you'll have them memorized. So, you can put that to good use. So, in this case, This is the one that turned out to be 196. Okay, here's why. So if you go to your calculator, second vars, um, number two normals, sorry, number four, three rather, it's I and V norm. And we did, these obviously earlier. Make sure you use the left area. So the first thing it will ask you for is area, which means left area, sigma. And you put in the numbers, and you'll see that it is indeed 1.96. All right, that goes into obviously this part of the formula. What about the rest? So remember, we calculated the P as 0.7048. And the sample size was 105. All right, let's go back. Yes, 105. So of course, the first thing you want to do is calculate the margin of error. Let's do that real fast. Point 0.0445. And the range then is from 0.6603 up to, oh, whoops, hold on. Obviously, I made a typo. 74.93. That's my 95% confidence interval for the true proportion of restaurants that offer the vegetarian option. Is that it? Oh my God. Now, I would like to point out here, though, that there are shortcuts built into this calculator, which we've kind of been glossing over here. Um, this one, you're at home, you can decide which one to use. If I wanted to do this a little faster, you go to the button Stat Tests. Stat is a separate menu. Scroll over to the right for tests. The one you want here is number one, prop. It's not right. It says one here. It's actually number, I don't know how that happened. It's actually A. And you hit enter, and it's basically just going to ask you for all the details. N is 74. 105 is N. Level means confidence level. The one we just did was 95. Let's jump ahead to that one. It doesn't have that one separately. Okay, let's do that. If you put 95 in your calculator and hit calculate, you'll see that what we have is something a little different here. Let me just double check something. Oops, something went wrong here. I apologize, like I goofed. Um, this margin of error is not correct. Let me fix that. I don't know exactly what happened here. I'm sure I made a typo. But yeah, something's not right here. Let's go back and fix this. One minus that, that's probably where I screwed it up, is 2952. Six, so let's fix that. All right, I'm going to try this one more time. You know what I did? I forgot that 196. Oh, well, it's easy to make mistakes. Oh, sorry, that's not right. We're subtracting. And then what? Let's see what that gives us. Point, yeah, this is much better. 6176, that's more like it. 792. Yes. So going back to the special shortcut, um, if you follow these steps, well, they've got 90. All right, we'll change it to 95. Stat tests a prop z int. You'll get, yeah, that's more like it. 6175 something and 792 something. Okay, perfect. So, you can decide which one you want to use. But when you're first learning it, you really should avoid the shortcuts just to make sure you understand. So at this point, you are now really caught up with the things you should remember from Stats 1. It's not that there aren't any other concepts that you should know, but these are the ones that we're going to start seeing right away in Chapter 9. First introduction to a very important topic called hypothesis testing. Now, having said that, because it's our first day back, normally I would have had a bit of a break in there somewhere. This is a very long class, but I think because it's the first night back, I think that it is sufficient for us to have reviewed, and we probably should start from scratch tomorrow with the hypothesis testing chapter, which is 9, especially since it's getting kind of late here. So I think we'll stop right here, and tomorrow when we pick it up, we'll sit down and do the introduction to hypothesis testing, keeping these right in front of us at all times. And you'll see right off the bat, you'll need to remember all these concepts about confidence intervals, the normal distribution, and the T. So all this review, I think you'll agree, was a huge help. For now, we'll stop. Now, I'm going to record, the recording is going on as we speak, but it has to be processed into an MP4 file. And I have to leave right now. So that's going to take a while. So probably not till tomorrow. This stuff will get posted on Blackboard, but it will get posted in case you miss something. And then we'll pick it up again tomorrow night. How does that sound? So, yeah, so hopefully all of this came flooding back. All of these are very pleasant memories from Stats 1. And so now we get to do something completely new tomorrow, although you'll see it is directly related to confidence intervals. But it's an important idea that we'll see over and over again throughout Stats 2. Okay. So, all right. Unless there's any last minute questions or anything, I will see you all tomorrow. By the way, I think maybe tomorrow we'll aim for 6:30. I'll tell you why, because I have to do a lot of traveling around this week. And I think I can make it by 6:30, but if I get here a few minutes late, you'll wait for me. Okay. So this way we don't have to start quite so late. And then remember, Thursday, I'm just going to make a recording, and then next week we can start at 6 again. Okay, which I think you'll agree is much better. So, all right, and I'll remind you by email about all of this. Anyway, so I guess I'll just see you all tomorrow night then. All right. All right. Good night.
Thank you.
Thank you.
Bye. See you later.
Thank you.
Thank
You're
you.
welcome. All right. Bye.
Thank you, Professor. I'm sorry I was late tonight.
Oh, it's okay.
Yeah, I thought it started tomorrow and then I saw the email late, so I joined as fast as
Yeah.
I could.
Well, I thought it started yesterday, so
Really?
yeah, I
Yeah.
did.
Yeah.
Anyway, so we're all set now.
Okay, thank you so much. I'll see you
All right.
tomorrow.
I'll see you tomorrow. All
Have a
right.
nice
Good
night.
night. All right. Bye.